every large language model, every image generator, every recommendation algorithm. At their core, they all share one thing, a structure called a multi-layer perceptron, or MLP for short. MLPs have been around since the 1980s. They're so fundamental that most researchers don't even question them anymore. They're just the default. But in April 2024, a team from MIT published a paper asking, what if we've been doing this wrong the whole time? What if there's a better building block, one that's not just more accurate, but one you can actually look inside and understand? That paper is called KN, Kolmogorov-Arnold Networks. And today we're going to break down exactly what it does, why it matters, and honestly, where it falls short too. Before we get to KN, we need to make sure everyone's on the same page about MLPs because a lot of explainers skip this and then the rest doesn't make sense. Imagine a neural network as a series of layers. Each layer has nodes. We call them neurons. Information flows from left to right. Each neuron takes in numbers, does a little calculation, and passes a number to the next layer. Now, and this is the key thing to understand, there are two parts to what each connection does in an MLP. First, there's a weight, a number that says, how much do I scale this signal? Think of it like a volume knob. Second, there's an activation function, a fixed mathematical shape, like ReLU, which just means if negative, make it 0, if positive, keep it. The activation function lives on the neuron itself. So in an MLP, the weights are learned during training, but the activation functions are fixed. You choose them before training starts, and they never change. The justification for MLPs comes from something called the universal approximation theorem, which basically says, given enough neurons, an MLP can approximate any function. So MLPs are theoretically capable of anything. But theoretically capable and practically efficient are very different things. And this is where the paper starts making its case. Here's where things get interesting. KN is inspired by a mathematical result from the 1950s called the Kolmogorov-Arnold representation theorem. Two Russian mathematicians, Andrei Kolmogorov and Vladimir Arnold, proved something profound. Any complex multivariable function can be broken down into a combination of simpler single-variable functions, just added together. Now, this theorem was discovered in the 1950s, and people immediately tried to use it for machine learning, but it failed. Here's why. The theorem guaranteed these decomposition functions exist, but it said nothing about them being smooth. In the worst case, they could be fractal, infinitely jagged, which no computer can learn. So for decades, this theorem was considered theoretically beautiful, practically useless. But the MIT team had a different take. They said, look, most real-world functions in physics, in biology, in science are smooth. The nightmare fractal case is a mathematician's worst-case scenario, not what you actually encounter in practice. And they asked, what if we just built a network around this theorem anyway for smooth functions and trained it with modern techniques like backpropagation? That's KN. Okay, let's get into the actual architecture. The change KN makes sounds almost too simple. In an MLP, activation functions sit on the nodes, the neurons, and they're fixed. The edges just multiply by a weight number. In a KN, this is flipped. The nodes do nothing special. They just add up what they receive. The activation functions sit on the edges and, crucially, they are learnable. Every single connection learns its own custom shape function during training. There are literally no linear weight matrices in a KN. Every single parameter is part of a spline function on an edge. These learnable edge functions are represented as splines. A spline is a smooth curve made of pieced-together polynomial segments. The key property of splines is that you can adjust them locally. You change one part without messing up the whole curve. KN is MLPs on the outside, splines on the inside. It inherits the compositional learning ability of MLPs, plus the precision of splines for fitting individual functions. And here's the elegant result of this structure. Because each edge is learning its own shape, when training is done, you can literally look at the network and see what mathematical relationship each connection learned. You can visualize the whole thing. That's the interpretability claim, and it's a real one. Now let's talk numbers, because this is where papers either live or die. The headline result is on solving partial differential equations. These are equations that describe how physical things change in space and time. heat flow, fluid dynamics, wave propagation. They're notoriously hard to solve numerically. KN achieves 100 times more accuracy on PDE solving compared to MLPs, using 100 times fewer parameters for the same level of performance. KN's error drops as n to the power of -4 as you add parameters. MLPs is much shallower. KN gets more efficient faster. Now, and I want to be really clear about this, these results are on scientific function fitting tasks. Small, structured problems where there's a clean underlying mathematical relationship. This is not KN beats GPT-4. The domain is AI plus science, and that's where these numbers hold. There's also a significant catch. KN trains much slower than MLP. Because every edge is a whole spline function instead of a single number, training is roughly 10 times slower with the original implementation. The community has since built FastKN, which gets this down to about 2 times slower, still a real cost. This is my favorite part of the paper, and I think it's genuinely exciting for science. After training a KN, you can look at it. You can see what each edge learned. And because the functions are smooth splines, you can then ask, does this shape look like a known function? Does it look like a sine wave? A logarithm? An exponential? The paper demonstrates this with 2 real examples. In one, they train a KN on data from knot theory, and the network independently rediscovers known mathematical relationships between knot invariants. In another, they use it on data from Anderson localization, a quantum physics phenomenon, and the network learns to represent the physical relationship accurately, in a form that a physicist can inspect and recognize. It's like the difference between a black box that gives you an answer and a colleague who shows you their work. KN doesn't just predict, it shows you the mathematical skeleton it found in the data. The authors call KN a collaborator for scientists. I think that's exactly the right framing. This is not about replacing deep learning for language or vision. It's about giving researchers a new kind of tool for understanding quantitative data. Okay, let's be honest, because the hype around this paper when it dropped was enormous, and not all of it was warranted. A follow-up paper called KN or MLP, a fairer comparison, ran controlled experiments across real machine learning tasks. The conclusion, KN only clearly beats MLP on symbolic formula representation. On vision tasks, NLP tasks, audio tasks, MLP wins or ties. Other researchers found KN struggles with noisy data and irregular functions. The spline representation, which is great for smooth scientific functions, doesn't handle noise as robustly as MLPs with dropout. And the training speed problem is real. Even with FastKN, you're paying a cost that makes scaling to large models expensive. So, KN is not an MLP killer. It is a specialized tool, and a genuinely excellent one, for structured scientific data where interpretability matters and the underlying functions are smooth. That's a real and valuable niche. But don't expect to see a GPT built on KNs anytime soon. The community response to this paper was remarkable. Within weeks, developers had built a whole ecosystem around it. There's FastKN and FasterKN. There's ChebyKN, which replaces splines with Chebyshev polynomials. There's GraphKN for graph neural networks, VisionKN for image models, and WaveKN using wavelet functions. The original code is open source. Pip install Python, and it's worth playing with if you work with scientific data. The deeper story here is about the tension at the heart of deep learning: accuracy versus understanding. MLPs are powerful but opaque. KNs trade some of that power for transparency, and in the right domain, that transparency is worth more than raw performance. That's the KN paper. Links to everything are in the description. If you want me to go deeper on any one section, let me know in the comments.